Good morning to all participants and good morning to our expert, Professor Dr. Parimalkar sir, on this fourth day of our FDP. And I welcome our expert once again, Professor Dr. Parimalkar sir from IIT Indore. And I also welcome our chair for the session, Dr. Sahadev Roy sir. He is from ECE department. He has been there at NIT Arunachal Pradesh since 2012. He has done his research in ECE from NIT Arunachal Pradesh. His research includes conventional topics in ECE, including biomedical image processing. He's also involved in robotics training. So welcome, Sahadev sir. Welcome you. In this short notice, you have come. Okay. So welcome once again, Sahadev sir. And I also welcome our all participants to this fourth day of our FDP. So on behalf of our director, Professor Dr. Pinkeshwar Mahanta sir, NIT Arunachal, Department of Basic and Applied Science. Of course, our sponsors, Atal AICTE, and on behalf of myself and the session chair, I invite all participants. Sadeh sir, if you want to tell a few words, you can join us.
Good morning, all. Respected expert from IIT Indore, Professor Parimalkar. We are happy to announce that this session will be attractive, and in this pandemic situation, this type of session is required to cheers us because we are all in a quarantine in house. So I hope that this session is interesting, and thank you, sir. Please.
Okay, thank you.
Yes, sir.
Okay, thank you. Thank you. Okay, good morning, everybody. So today we are going to talk about molecular dynamics simulation and Monte Carlo simulations in this first half, and second half I have another talk. So there I will show you the application of combining molecular docking that I talked about it in previous lectures, and molecular dynamic simulations. This combining these two, how we can study protein drug interactions, and I will show you some example of this COVID-19 only, okay? But the application part I will show in the afternoon. So morning part is mainly devoted to the theory part, okay? So now, so when this Nobel Prize in Chemistry in 1998, it went to theoretical chemist actually, okay? So that's for density functional theory. They got it. So it was written in this famous economist newspaper that in the real world, this could eventually mean that most chemical experiments are conducted inside the silicon of chips instead of the glassware of laboratories. Turn off that Bunsen burner. It will not be wanted in 10 years. Okay, so that was said in 1998, but now it is 2020. Still, we need experiment because there is no alternative to experiment. Okay, but the goal is in computational biology or in computational biophysics is to minimize the role of experiment. Okay, I mean, we want to predict the structure and everything computationally, and later on that can be validated by experiment. Okay, we want to reach to that level of accuracy. Then in 2013, okay, Professor Martin Karplus, Michael Levitt, and Arya, it's not Warsel, sorry, it's Arya Warsel, okay. So these three gentlemen got Nobel Prize again in chemistry, and this time the Nobel Prize was given for the development of multi-scale models for complex chemical systems. Basically, they work on biological systems. Martin Karplus developed charm molecular dynamics package. Michael Levitt and Arya Watson, they don't have any software, but they generally work on computational biophysics, okay? An interesting thing about Martin Karplus, you know, he was Austrian actually, and during the Second World War, so Germany was ruled by Hitler, and Martin Karplus was Yehudi, okay, Jews. So, and when Karplus was 8 years old, he had to fled from his native country, Austria, and whole family went to America, okay? And then when he turns 80 and he got the Nobel, think about it. He could have died at the age of 8. They just survived. They fled away from Austria. And later on, he became one of the finest computational chemists or computational biophysicists of 20th century. And Michael Levitt and Arya Warsel, they are all his postdoc actually. They all worked with him. They are somehow related. And all of these three gentlemen are Jews. Okay? So Martin Karplus is from Harvard, Michael Levitt from Stanford, and Arya Warsel is from Southern California. That's Hollywood. Okay? So they got it for multi-scale, developing multi-scale models. So today we are going to talk about multi-scale models. So what is multi-scale model and why do we need multi-scale modeling? Okay? Since biochemical processes are inherently multi-scale in nature. Why? Because it occurs on different length and time scale. For example, think about protein folding process. Okay? Protein can have different size ranging from small polypeptide chain to a very large multimeric complex protein. Okay? So that means their length scale varies. That's the spatial scale. Now think of the temporal scales. So the protein folding itself can occur from microsecond to millisecond time scale, and in rare cases it can go up to second time scale. So you can see that the length scale can vary from several angstrom, and the time scale also varies from millisecond to microsecond time scale. And certain chemical reactions also occur in the picosecond time scale, or sorry, picosecond time scale also. And the vibration of hydrogen atoms that occur in the femtosecond time scale. So you see that modeling such a complex system is not that easy because all things are happening at different time scale. When you look at a particular atom, say for example, you are looking at the hydrogen atoms, they are vibrating at femtosecond time scale. But now when you look at the global picture, okay, now when you are studying the conformational change of the protein is composed of a bunch of atoms, but when you look at the protein, then you see that, okay, there is some conformational changes that occur at, say, microsecond time scale. So one atom is vibrating at femtosecond time scale, but certain conformational transition occurring at microsecond time scale. Now you have to cover the entire breadth from femtosecond to microsecond time scale if you want to really study that thing. So that's a big challenge, okay? So generally, these atomistic simulations, that's why it's very hard to cover this entire spatiotemporal scales. And that's why different, generally we restrict our molecular dynamic simulation, atomistic molecular dynamic simulation to small proteins. Now with the advent of graphics processing unit, okay, GPU card, we are able to study bigger system, but at least 5-6 years ago, that was not the case. We are restricted to only 100 of nanosecond only, okay? So now how do you overcome all these things? So we developed different kind of models for that one. We have quantum mechanical model, molecular mechanics, that's the classical mechanical model, then core scale model, mesoscale model, okay, all this. So the core scale model I'll talk about tomorrow. Okay, that's the final lecture I will have. That's the recent advancement technique. But just to tell you that all the methods in molecular modeling, we are developing it because you cannot, there is not a single magic method that you can utilize to study different biophysical phenomena. No, you cannot, because different biophysical phenomena occur at different length and time scales. A single method cannot encompass all those possible spatiotemporal scales. Okay, so that's why we develop a lot of different techniques for that one. So the main problem, I told you yesterday also that this is the main problem, this figure. Okay, this is the free energy surface of proteins. And this is a very rough free energy landscape. You can see that. You want to reach to the position M, that is the native state. Basically, it's a global optimization problem. And you are got stuck somewhere in this local minima. How to get out of that local minima and reach to the native state? That is the main problem. Okay, so it's basically an optimization technique that you need to develop. And in physics, we call it sampling. This is the phase space we want to, and the phase space is a 6n dimensional space because 3n coordinates, okay, n is the number of particles or atoms. 3n is the, that is the XYZ coordinate, okay, that's the position coordinate, and then you got another 3 coordinates from momentum space, Px, Py, and Pz, okay. So the phase space is nothing but constitution of this 6n dimension of position and momentum. So MD simulation basically runs on this space. This is called phase space, and you are sampling. Okay, you are visiting all possible states. If you can visit all possible states, then your simulation is perfect. Okay. Otherwise, of course, there could be a problem. But we will. But if the ergodic theory is ensured, then maybe microsecond timescale simulation is also good enough. Anyway. So molecular dynamics, basically many physically based simulations model easily observable real world phenomena, but molecular dynamics simulation model things too small for us to observe directly, because you can say that molecular dynamics is nothing but a movie. Okay, it's a movie at the atomic scale. You are studying how the atoms are moving, okay, and how they are interacting with each other as a function of time. With time, what is going on? Because that's the real thing happening in your body. Proteins are, or any biological macromolecules, they are flexible molecules. And since we are at room temperature, so that means there is some thermal energy there already, okay? So if there is some energy, then of course all atoms will vibrate. They will move around. There will be translational motion, there will be vibrational motion, and there would be rotational motion. All possible motions are possible. Okay, so there is dynamics in it. So of course, if there is dynamics, then you can model it via time-dependent differential equation. That's exactly what you do in molecular dynamic simulations. Now the question is, why don't you use quantum mechanics? Why we are interested in classical mechanics? Okay, so you can use, of course, quantum mechanics, and there you have to solve the Schrodinger equation. Basically, this equation, you can solve it to get it, but it's very hard to program and takes more computing power than anyone has. Generally, the quantum mechanical calculations are restricted to only 100 of atoms, maybe 100 to 200 atoms, and the time scale is limited to femtosecond to picosecond time scale. But you know that the protein folding or any other conformational transition in protein that occurs at microsecond to millisecond time scales. So picosecond is 10 to the power minus 12 and microsecond is 10 to the power minus 6 seconds. So basically you can see that there are this 10 to the power 6 number of more iterations you have to conduct it to reach to that time scales. And it takes enormous amount of time in if you want to do it. using quantum mechanical method. I'm not saying that you cannot do it. You can do it, but at the cost of time. You may need several, you need a couple of years to reach to that kind of level. So people don't use it. Generally, quantum mechanics is used to study certain chemical processes like chemical reactions, okay, enzymatic reactions that occurs in the picosecond time scales. Okay, and also if you want to use the time evolution, then you have to use time-dependent Schrodinger equation for it. So that's why instead of quantum mechanics, we can use classical Newtonian mechanics to model our systems. So this is a simplification of what is actually going on and is therefore less accurate. But to alleviate this problem, we use numbers derived from quantum mechanics for the constant in our classical equations. Okay. Now this is why molecular dynamics method is called multiscale method. Because you are deriving certain parameters from quantum mechanical calculation, which is higher level, okay? And then you are transferring those parameters to a coarser level, that is atomistic level. So this is called serial multiscaling method, okay? So you did certain calculations of quantum mechanics, then you are using that parameters and transferring it to classical mechanics. And you are assuming that it will work. Actually, it works. Okay, it's not that easy that it will work, but it is working. Okay, probably that's why they got Nobel Prize for this. Combining this thing is not that easy actually. Anyway, so that's why this is called a serial multiscale approach. Now, if you want to study the dynamics of atoms, that means the time evolution of their position. So then, for each atom in every molecule you need the position coordinate, okay, that is R. So R is X, Y, Z coordinates, okay. Then momentum, you need to know the mass and velocity. And then for electrostatic charge-charge interactions, you need to know the charge of each atom. And you know that all atoms are bonded. So you need to know the bond information also, okay? That means which atoms, bond angles, etc. actually, okay? Whether they form single bond or double bond, and what three atoms are forming the angles, what could be the possible allowed regions of angles, and how much you want them to allow them, this angle can vibrate. That also you need to control because it cannot vary much. Okay, so all this kind of thing you need to know. Okay, the penalty things you need to know for molecular dynamics simulations. Okay, so now to run the simulation, we need the force on each particle, and force is mass time acceleration. Okay, now what is now this force also you can calculate it from the potential energy. So force is the negative gradient of potential energy. Okay, so then F is equal to mass time acceleration equation boils down to minus dv dri is equal to mi d2ri dt2. Okay, because acceleration is d2r dt2, velocity is dr dt, so acceleration is d2r, double derivative of position with respect to time. That is your. So now what you get? You got a second order differential equation. Now this is a coupled differential equations. Okay, and the number of equations that you need to solve simultaneously would be 3 times 3n, okay, where n is the number of atoms present in the system. So now generally when you simulate or study the dynamics of any biological macromolecules, we need to consider the effect of solvent also. Okay, so that's why you need to immerse the solute into a solvent box. It could be water or it could be membrane. So now if the total number of atoms including water molecules is 1 lakh, then you have to solve 3 lakh coupled second order differential equations simultaneously. Okay, we are talking about that kind of problem. Now, if you want to model the whole cell, the smallest cell, okay, at the atomic level, then you may have 100 million atoms. If you have 100 million atoms, then you have to solve 300 million coupled differential equations simultaneously. Okay, so the complexity increases with the increasing number of atoms. Okay, so that's why initial days when there was no large supercomputing facility available, we could not run it for longer time scales. Very short simulation we ran. Then early 2000, we used to start running longer time scale. Then in 2010 also, we could run simulation for 100 nanosecond. Okay, or 200 nanosecond in 2010s. Then in 2012 onwards, these GPU cards came into the market. They came into the market for the gaming purpose. Okay, because for gaming, video games, they need very high intensity graphics processing card. So this GPU card, then we started coding in GPU instead of CPU. Okay, because GPU has a lot of threads available, so we can use those threads for parallelization purpose. So then we started gaining actually. And right now, in the market, okay, in 2020, we have excellent graphics card are available. So for example, Tesla V100 graphics card. Okay, so that's one of the fastest graphics card available. And if you have 100,000 atom, okay, so that means 1 lakh atom. And if you use a single processor, okay, only single processor and one V100 graphics card, then per day you can run simulation more than 100 nanosecond. So 10 years back, to run this 100 nanosecond MD simulation of 1 lakh atom, it takes us more than a month. And now we can achieve it in a single day. Okay? So that is the advantage. Because of this technological advancement, we can run bigger simulation for a longer time scales. Anyway, so this is our challenge actually, that you have to solve this many number of coupled differential equations. Okay. So now the main part then here is the potential energy. Okay, because you want to calculate the force acting on each atom, and force is nothing but the negative gradient of potential. So we need to find out what is the potential energy. Okay. In in computational biology, we don't call it the potential energy, we call it force field. Okay, and in physics, we call it Hamiltonian. So the chemists love to say it, or chemists and biologists, they call it force field, and in physics, we call it Hamiltonian. Anyway, so a single atom will be affected by the potential energy function of every atom in the systems. So you need to consider some bonded neighbors with which atom it is forming bond, direct bond it is forming. Okay, there could be angular bond, there could be the single bond. Okay, and sometimes it can have bond with 4 atoms also. This is called the torsional angle. Okay, they can move like this way, they can move. Okay, 2 different planes, they can move it. And then there are non-bonded atoms. So either other atoms in the same molecule or atoms from different molecules. Okay, so that means the total potential energy is the sum of bonded interactions and non-bonded interactions. Okay, so there are 2 potential functions we need to be concerned about between the non-bonded atoms. One is the van der Waals potential and other one is the electrostatic potentials. Both of these interactions are long-range interactions. That's why if these two interactions actually helps to keep the protein or biological macromolecule structure in compact. Okay, because it interacts with an atom which is even beyond 10 angstrom away from it. Still, the interaction you need to consider for that one. Okay, so these long range interactions, so you need to consider those things. And van der Waals is also very important. You know that it also attracts each other. But when they come very close to each other, then there is repulsive force. Okay, so it helps atoms to attain an equilibrium position, basically. Okay, so overall, the job of these two forces is to make a compact structure. And this van der Waals, as I said, that once the atoms are close enough to have overlapping electron clouds, they will repel each other with astounding force, because you cannot allow the overlapping clouds, electron clouds, because of Pauli's exclusion principle. Okay, that's the quantum mechanical phenomenon. So we model this van der Waals interaction generally using this Lennard-Jones potential. Okay, so you see that this equation has a term of r to the power 6 and 1 by r to the power 6 and 1 by r to the power 12 term. Okay, this is a Lennard-Jones potential. You can use the same thing. You can model it using there are other forms of van der Waals interaction energies there. That is called, say, London's equation is also there. You can use that thing also. But the most popular is the Lennard-Jones interactions, because this is easier to model it computationally and very fast. So in this van der Waals potential, this 1 by r to the power term is the repulsive part, and the attractive part is 1 by r to the power 6. And the balance is shown by this red curve. Okay. And the equilibrium position is the minimum position that you can see here. So generally, we use this formula Vr is equal to 4 times epsilon. That equation generally we use it to model this van der Waals interaction energy. And the next is the electrostatic potential. I mean, you know that these are all school level physics. So basically Qn and Qi and Qk are the two charges. So of course then the electrostatic potential will be Qi Qk by r. R is the distance between them. Okay, so this is simple Coulombic interactions. But the difficult part is that both these interactions are, I mean, in your MD simulation, most of the times are taken by these two terms. Bonded interactions are easy to calculate. And these are the most time consuming part. Why? Because these two interactions are pairwise interactions. Each atom can form a pair with if there are n number of atoms, then one atom can form n minus 1 pairs. Okay. So that's why you have to consider the all pairs. So that's why this interaction is the most time consuming, the non-bonded interactions. Okay, and this is also very vital because it helps to make the structure cohesive and more compact. So the Coulomb's law is taking care of course, this electrostatic potential energy. This is the Coulombic force, and this is the Coulombic potential energy. Anyway, so then the non-bonded interactions is the sum of the van der Waals and electrostatic interactions, and then we come the bonded terms. Okay, so now in molecular modeling, we consider that each atom is connected by spring. Okay, so this is the simple concept that is derived from condensed matter physics, from the lattice model. Okay, how we treat the crystal. From the same concept is applied here. Okay, so the bond could stretch along the bond. Okay, so it can be like that, and bond can bend also like this. Okay, and then there is rotation also. So the rotation, basically, this is the rotation we are talking about. So the bonded interaction is sum of the bond stretching, angle bending, and dihedral angle. Okay, this is called the torsional angle, basically. The rotate along a bond, that is called torsional angle. So these are the three different terms you need to take into account. So generally, we model all these bonded interactions by simple harmonic potential energy. Okay, so that's why bond stretching is Kb into B minus B0 whole squares. Okay, B0 is the equilibrium length that you get it from your quantum mechanical calculations, and B is the as a function of time that is varying. Okay, so and this Kb, that is the binding constant, that also you derive from the quantum mechanical calculations and match with the experiment also. So this Kb is the it determines the shape of the potential well. I told you that the potential well could be, although it is simple harmonic, but it could be narrow simple harmonic well, or it could be wider. If you make it too wide, then the atom will fluctuate a lot. If you make it too narrow, then the atom will be very stiff. It will have no motion. Okay, so if you use something like a very steep wall, so how the atom will move? There is no space for wiggling around. So you have to make a judicious thing. Actually, this Kb, this parameter actually controls that thing. How much flexibility you want to provide to the atoms. You should not give it too flexible that the bond length, the stretching is so high that chemically it is not permissible. Okay, that they are separating from each other. So that should not be the case. But then what is the drawback here? You're saying that you have a simple harmonic potential, but in reality, there could be an harmonic presentation also. Okay, so we are not taking into account that thing here. Okay, so we are just saying that they have a simple harmonic motions. So we make a lot of approximations in this process, okay, so that the simulation is faster. And same thing for bonded, for angle bond bending, that is the angle bending, okay. So we use the same simple harmonic motion. We are neglecting any anharmonicity present in your system. Okay, so here the main important parameters is Kb, K theta, and B0 and theta 0. These are the parameters that you need to supply. Okay, and those are generally calculated from the quantum mechanical calculation and then later on matches with the experiment. So that's why I am telling you that this is called multi-scale in nature, because you are calculating something at higher level and then transferring it to a lower level of representation, and you are thinking that it's going to work, and it works actually. And then this torsional, the dihedral angle, okay, so that one you calculate it using this kind of harmonic potential again. So then overall, your potential energy function looks like this. It is a sum. The first term is the van der Waals energy. Second one is the electrostatic energy. Third one is the bond stretching. Fourth one is the angle bending, and the fifth one is the torsional angle movement. Okay, so these are the 5 terms generally constitute the potential energy. And you have to take a gradient. Okay, you have to calculate the force on each atom. That means you have to take a gradient of this function for each atom. Okay, so that is the complexity we are talking about. So since it is second order differential equation d2r dt square, and we want to get r as a function of time, of course you need to integrate it to get r as a function of time. So generally Euler algorithm we don't use it because of this 1 by r to the power 12 term. It becomes very unstable, and Runge-Kutta and midpoint algorithm could be good enough, but they are very slow, so we don't want to use it. Okay, As I said that in molecular modeling, you always have to make a compromise between speed and accuracy. Okay. So generally, the algorithm that is most widely used is called the Verlet algorithm. Okay, this is a French mathematician. He developed these things. So yeah, so our t plus delta t. T is the current time, delta t is the future time. We want to advance because we want to see at t is equal to 0, this is the position. By molecular dynamics simulation, we want to calculate at t is equal to 0.5 femtosecond, what would be the position of each atom. That we are interested. Okay. So then you do the Taylor expansion, RT plus delta t. If you just do the Taylor expansion, you will get this thing. And then you take a backward step. Then calculate RT minus delta t. Okay. Then you again do the Taylor expansion. And then you sum these two together. Then what you get actually RT plus delta t plus RT of t minus delta t is equal to 2RT plus AT. AT is the acceleration plus delta t whole square plus this is the higher order errors that you should neglect it. Now delta t is the time step, okay, integration time step that you are using. So if you want to move to the future state, okay, RT plus delta t, then you need to know that is 2 RT, okay, so you need to know the current position minus RT minus delta t. You need to know the backward step position at time t minus delta t also, okay, and then you need to know the acceleration at the current time. If you know these three things, then you can move your atoms to a time step t plus delta t. Okay, now you can interchange these things. Okay, you can replace in the first equation t by minus t, and here the same thing like here I'm saying in the first equation you can replace t to minus t, and in the second equation also you can do the same thing. You need to make sure one thing that the Newton's second law of equation is a time symmetric equation. You have to make sure that you can go back. You can go back also. That is the beauty of this equation. Okay, so that thing should also be preserved in your integration algorithm. Not only you can move your atoms to the future step, but you can go back also. Anyway, so now we need to know the velocity. Why do we need to know velocity? Because we need to ascertain the temperature. Now, how do we get the temperature? Temperature can we get from the kinetic energy. Because from the equipartition of kinetic energy, we can calculate the temperature. Okay, this is statistical mechanical theory. I don't want to go into that thing. So the velocity you can calculate then from this. Okay, but in structural biology, you really don't care about the velocity. This is just for the simulation purpose because you are only interested in the structure. And what determines the structure? Only the position, x, y, z coordinate. That determines the structure, not the velocity. Okay, but you need to store this data. Okay, because you need to always calculate the temperature because you want to run the simulation at 300 Kelvin or 400 Kelvin in your desired temperature. Okay, so you need to monitor the velocity. We assign velocities following Maxwell's-Boltzmann distribution. Okay, and we assign it in a random manner. Each atom is given initially we assign velocity to each atom in a randomized manner, but we make sure that it follows Maxwell's-Boltzmann distribution. Okay. Now you see that in the velocity calculations there is a second order of error. So there are variations of the Verlet algorithm such as the leapfrog algorithm which seeks to improve velocity estimations that we talk. Now in pictorially we can show this Verlet algorithm like this. Okay, so given current position and position at end of previous time step. So these blue lines are given. I mean the blue boxes are given. Okay, and you want to find R t plus delta t, which is a green one. So how do you do this? So first you compute the force at the current position. Okay, so just check that I have drawn an arrow so that you calculate. So when you calculate the force, then you can calculate the acceleration. Acceleration is equal to force divided by mass. Okay, so you can get it. Then, of course, you can using this equation and you can move to the next step. Now, to move to the next step, so t plus delta t will become r of t. Okay, and r of t will become r of t minus delta t. Just like that, you move your atoms following these steps until your simulation is converged. Okay, so just you repeat this step and iterations. If you want to run it, so generally delta t is 2 femtosecond we use, and if you want to run it for 1 microsecond, so you need to move from 10 to the power minus 15 to 10 to the power minus 6. So you have to run for 10 to the power 9 iterations. You have to repeat this thing. Okay. So the advantage of Verlet algorithm, it is simple and effective. Of course, you need low memory and CPU requirements. Okay, don't need to store velocities or perform multiple force calculation. It is time reversion, that is mandatory, and very stable even with large numbers of interacting particles. And cons, not as accurate as RK. We never calculate velocities actually. Actually, who cares? Because we are interested in structural biology, we are interested only in the position structures. So that's the thing. So any simulations that when you run, say the MD simulations, first we need to check whether this algorithm is correct or wrong. For that one, we need to make sure the basic physical law is not violated, and that is the conservation of energy. The sum of kinetic and potential energy at a particular temperature should always remain fixed. If with time, the total energy of your system is increasing at constant temperature, that means your algorithm is flawed. You need to make sure that thing. Okay, so you should always monitor the total energy as a function of time, whether it remains constant or not. Okay. Now next is leapfrog, and the leapfrog you have actually, I don't want to go into all these things calculations. So basically there is this half time step difference. Okay, there you have RT plus delta t, but here you can see that Rn plus 1, that is RT plus delta t is equal to Rn plus Vn plus half into delta t. So there is a half time step difference. In previous you have delta t, the full time step, but here you have a half time step. So there is the Vn plus 1 is the velocity at time t plus delta t by 2. And the position that you are calculating here is R at t. So there is always this half time step difference. The velocity and the corresponding positions are not from the same time steps. There is always this half time step difference. So that's why in this screen, maybe you may think that it's very difficult to keep the total energy fixed, but that's not the case. Within the error bar, the total energy remains fixed. So this is also a very popular algorithm, but the most popular is the leapfrog algorithm. Okay, so here you use Rn to calculate Fn, and then you use Fn and Vn minus half to calculate Vn plus half. Okay, that means that is V at t plus delta t by 2, and then you use this Rn and Vn plus half to calculate Rn plus 1. Okay, this is how you calculate the velocity. Instantaneous velocity at time t is basically the average of these two velocities. That's how you do it. Advantage, well, improved estimation of velocities. Because in the previous one, we saw that there is a second order error, but here we are not seeing that kind of thing. Okay, and then direct evolution of velocity gives a useful handle for controlling the temperature in the simulation. Only that is the purpose, otherwise it's fine. And disadvantage is the velocities at time t are still approximate because you are using R from time t, but you are predicting and you are calculating the velocity for t plus delta t by 2. So there is this half time step difference. Okay, so and also it's a computationally a little more expensive than Verlet. The better the model is, the larger the computation time would require. Okay, so that thing you should always remember, and this is how pictorially I show it. Okay, given the current position and velocity at last half step. Okay, so you just check it that R, V, and F, so there is always this half step difference. Okay, if you just look at the blue patches, so you see that thing. Okay. So using that, you calculate the velocity at at time t, and then you use it to calculate the velocity at Vt plus delta t by 2, and then you all these things to calculate R at t plus delta t. So you see that the position corresponds to R of t, but the velocity corresponds that you are using, that corresponds to time t plus delta t by 2. So the difference between position and velocity is delta t by 2. Half time step difference is there. But in principle, both should correspond to the same position, no? Same time. The position and velocity should correspond to the same time, but that's not the case here. That is only the thing. Yeah, okay. Then of course you can move like that, okay? Just a repeat iterations kind of thing. So that is the overall idea of this thing. And the final one is the Velocity-Verlet algorithm. This is the most accurate, okay? But here you store position, velocity, and acceleration all at the same time t. That is the best thing, because that's what you want. You want position, velocity, and time at time t. There should not be any time difference. So this is the best method. But imagine now you need a lot of memory now, because you are storing position, velocity, acceleration, all you are storing. And end of the day, you are only interested in the position, because you are interested only in the time evolution of the configuration. Because you are interested in the dynamics of structure, how the structure evolves with time, that you are not interested. So the rest you are not that interested. Those are just to control the simulation, that's all. So you need a lot of memory here. And since you are calculating everything and storing, so you need a lot more computational resources. But this is the best accurate, but we don't use it because it is time consuming. Okay, so this is again this pictorially you can use it. Okay, so you know all this R, V, and F at time t, and then you use this equation below. Just you move the atom to R t plus delta t positions. Okay, then this all this R, V, and F. For the next step, this you need to calculate it t plus delta t, so that will become your R of t. Then again you move it, just repeat it. Okay, the current position will become the previous position for the next step. That is the main thing, just remember, and you keep iterating this thing. So generally these are the three algorithms. Those are implemented in different molecular dynamics software package. Okay, and in AMBER we use Verlet algorithm. CHARM has leapfrog, Verlet, and as well as Velocity-Verlet. All these things are implemented there, but generally they use leapfrog algorithm. So this flow diagram I already told you about it, so I don't need to talk about these things. Okay, this flow diagram. So that is the basic of molecular dynamics simulations. Okay, now let's talk a little bit about Monte Carlo simulations also. Okay, so in the widest sense of term, Monte Carlo simulations mean any simulations, not even necessarily a computer simulation, which utilizes random numbers in the simulation algorithm. Okay, and the term Monte Carlo comes from the famous casino in Monte Carlo. That's in France actually. And then another closely related term is stochastic simulation, which means the same thing as Monte Carlo simulations. So here, this thing actually, this paper that this Metropolis actually Monte Carlo, we call it MCMC. So this is a famous paper. You can look at it. That was published in the Journal of Chemical Physics in 1953. Okay. That's the seminal paper where this Monte Carlo concept was introduced. So the approach is to calculate the energy EI and then randomly move an atom or molecule to give a new energy, EJ. Okay? Then decide whether to accept or reject the move. Now, whether you will accept or reject the move is actually probabilistic. It's random. Okay, so that's why this method is good, because you are not inserting any bias in your simulations. It is random just. So that's why it is a better sampling process. But here you don't get anything as a function of time. That thing you need to remember, okay? So can easily extract thermodynamic properties within NVD canonical ensemble. So this is the expectation value A, okay? That's the observable, any observable that you want to measure. 1 by Q and then A e to the power minus EI by KT, okay? E to the power EI minus KT is, that is the Boltzmann factor. And Q is called the, what is called, I forget this thing. So basically, Q you can calculate using this formula. So any observable, actually you can calculate from Monte Carlo simulation using this formula. And the same formula we use it to calculate any properties, any observable from MD simulation also. Okay, so this is the basic statistical mechanics. That's beyond the scope of this course. Okay. Rather, I would love to talk about these things, how we can use thermodynamics to understand the evolution of life and to explain biodiversity using second law of thermodynamics. Okay. Anyway, so maybe later we can talk. So the main thing is how do you select whether I'll go to the next step or not, next energy value I'll move or not. So as I said that in computational biophysics, the main problem is this, the figure that I have shown you. It is a very rugged free energy landscape, very rugged. We call it frustrated system, spin glass system. Okay, you have multiple local minima and you need to reach to the global minima. Okay, so you may always high chance that get stuck in those local minima. All these methods are generated to overcome this problem. How you can overcome, how you can jump the energetic barrier and reach to the global minimum. Okay, so if the new energy is lower, that is a more stable structure, then accept the move. So Monte Carlo, we always make sure that the next day we will take the new configuration, we'll accept the new configuration if and only it has a lower energy than the current configuration. Because lower the energy means stable the structure. So that means you are moving towards native structure. Okay, you are moving towards global minimum. So if the new energy is higher, that means that is less stable, then generate a random number between 0 and 1 and then calculate the probability, and the probability you calculate it e to the power minus ej minus ei divided by kt. Okay, only accept the move if the Pij is higher than the random number. Okay, so this enables the system to focus on the important configurations only, and you are not adding any inherent bias, because this probability you are calculating, but whether this probability will be greater or less, that you don't know, because you are generating a random number between 0 and 1 and then you are comparing with that. If it is more than, then you accept it, otherwise reject it. Okay, so over the time, basically your system may stay for a quite long time in the same stage before it moves to the next lower energy level, because it may be rejected, no? So that's why you need to run it for a long time to reach to the global minimum, or to ascertain that you have achieved convergence of your simulations. Another way of asserting convergence of simulation is to check the ergodicity. Okay, that is the time average should be equal to the ensemble average. Then you can say that your simulation has converged, and you can use equilibrium thermodynamic or equilibrium statistical mechanical method to calculate all observables. Okay, so that is the basics of Monte Carlo and molecular dynamics simulations, and in many cases actually we combine MD and MC together. Those hybrid approach also we take. I'll talk about that tomorrow. Okay. Anyway, today is already 1 hour. So now let us talk about little different things. Okay, Verlet algorithm is nearly always the best choice. It is very fast computationally. It requires little memory. Long-term energy conservation is excellent. As I told you, that you need to always monitor the total energy response up. Okay, time evolution of the total energy, and it is time reversible. That you need to make sure, because Newton's second law of motion is time reversible. That has that property. So you need to make sure that. And then other Verlet type schemes such as the leapfrog algorithm are also widely used. And higher order methods such as predictor corrector scheme, I didn't talk about it. Those are less common, although these are of course better method, but they are basically they increases the computational time prohibitively. So that's why generally we don't use those methods. Okay, Velocity-Verlet, predictor corrector, generally we don't use those things. Mainly leapfrog or Verlet algorithms are widely used for molecular dynamics simulations. Okay, and now another thing that is we should remember that the time step, because this delta t, what determines the delta t? The delta t is determined by the fastest motion present in your system. Now, the fastest motion in your system possessed by the hydrogen atoms. Okay. So if you look at the crystal structure, like yesterday you have seen it, when you get the crystal structure that you downloaded from the protein data bank, what you notice that there was no hydrogen atom in it. Why? Because in X-ray crystallography you cannot determine the position of the hydrogen atoms, because they are so fast moving, you don't get enough electron density from where you can ascertain their positions. You can get it only from the neutron scattering. But in India, there is no neutron scattering actually. Even in world, also 4 or 5 places they have neutron scattering. One of them is the Los Alamos National Laboratory, where I was a graduate intern. Okay, it is very costly thing also. So that's why the time step basically controlled by the fastest motion present in your system, and generally that is hydrogen atom. And hydrogen atom vibrational frequency is in the femtosecond time scale. That's why you use a time step delta t is equal to 1 femtosecond or 2 femtosecond. But think about it, if you can use larger time step instead of 2 femtosecond, if you can use 4 femtosecond, then your simulation will be so faster. It will take less time to move from the femtosecond to microsecond time scale. So tomorrow I'll talk how we can achieve this delta t is equal to 4 femtosecond, 6 femtosecond, even 20 femtosecond. How can we achieve? That we can achieve via core-scale modeling. Okay, so that's tomorrow we'll talk about it. So overall, just remember that generally in atomistic molecular dynamics simulations, we use a delta t of 2 femtosecond maximum. That is maximum allowed, provided you put a constant on your system. And the constant is that all bonds involving hydrogen atom are constant. You put a force on it. Okay, you don't let them vibrate so fast. End of the day, you don't care much about the hydrogen bond in protein. Okay, you are mainly basically those are generally not needed. You want to know the structure only, no? So hydrogen atom is not that important for that purpose. But often we have seen that if they take part in some kind of interactions, maybe then only you can. But otherwise, it's fine. It's not that important. Anyway, I may stop here. So in the afternoon, I'll continue to talk about different free energy methods actually. So I told you that talking is not the ultimate. Okay, whatever you are getting from the docking is fine. But later on, we should use molecular dynamics simulation coupled with advanced method to calculate the binding energy. So in the afternoon, I'll talk about one or two more advanced method, and then I will show you the application. I will show you some result that the result will be from the source code actually. Okay. So now, if you have any questions, just let me know.
Sir, thank you, sir. Sir, that topic was really interesting. So I believe I am audible, isn't it?
Yeah, I can hear you.
Yes, sir. Thank you very much, sir. I am very happy on my personal note, which I will talk in the after the participants' questions. Now I open this floor for questions and discussions among participants. Please.
So there is this question.
Yeah, participants, kindly you can ask questions through chat, or if you unmute and ask, then that will be better. Yeah, you just unmute and ask. See that you don't have two sources of watching this video, because echo is coming. You close at least one source, okay?
No, I mean predictor corrector method generally not belong to a class of algorithm designed to integrate ordinary differential equation. Okay, but generally this one was developed for actually for this kind of equations actually to find the velocity. There is second order of errors. To overcome all those things, this later on all these methods are actually developed. So not really to solve, I would say that second order differential equations, rather to focus on this particular problem. Okay. What is the major limitation of only Monte Carlo simulation? So when I'm in Monte Carlo, as I tell you, that you really won't get any time evolution property. So there is no time here. So if you want to study any property which is time dependent, okay, you are interested to see certain properties. So for example, you want to see how the solvent accessible surface area of the protein is changing with time. Okay, suppose you are studying the function, the protein folding problem. Okay, so when it folds, it becomes more compact, and the surface area should also decreases. Okay, so now you want to study how is it evolving as a function of time. Then how do you get it? You cannot get it. Otherwise, MC is pretty good. I mean, if you are interested to study these, say only the protein folding problems, say, okay, then it is fine. I would rather say that Monte Carlo is a better method for find a global minimum thing. Okay, so that's why we develop hybrid model. We combine now because we are interested. We want to get a time dependent. We want the time also. At the same time, we want to avail the advantage from Monte Carlo. So that's why we develop a method using Monte Carlo and MD simulation together. We call it replica exchange molecular dynamics simulations. We'll talk about it. Maybe if time permits, we'll talk about it. I am not sure about those things, but those are, isn't it? Those are generally used for the error calculation, jackknife, bootstrap, Those are for the error calculations generally we use it. No? Those are error method. Anyone?
Sir, yeah, I think participants, I believe you don't have any further questions. So I'm having some indications I need, sir, which I believe along with me, participants will also get guidance. Sir, whether you have some research papers for this study which you have made, so that one can go back and see these concepts repeatedly and try to understand it. My first question, I have 4 questions.
The paper, see, I will discuss some papers actually in the afternoon session. Okay.
Okay, sir. Okay.
Thank you, sir, for this wonderful session.
Shah sir, 1 minute. Yet I have not yet finished. My next question is, sir, can we? This simulations actually looks heavy. Can we do that in our desktop, or what is the desktop which you require? Minimum amount of technical capabilities which you require. Or one more question: we will simulate everything, and can we approach?
Sorry, I didn't. I couldn't hear you the last line, or you can. So okay, let me answer this question. So this is a very valid question. Let us talk about the history actually. So when these MD simulations actually, came out, of course, as I said that you need a very large computational resources, because with the increase in your system size, you need to discouple differential equations, and you need a lot of memory, of course. So previously that was the case till 2010, 2012, and it was a drawback for researchers from India or any other developing country, because we don't have supercomputing facility. When I was in US, I always had access to Texas supercomputing system, that is called X3, okay? So I can use always thousands of processors. So there was no level playing field. And only those who have access to Blue Water or Eugene P, so then they can do all those kind of simulations for a couple of 100 nanoseconds. Okay, I'm still saying that till 2010 to nobody used to do these microsecond time scales. It's only 100 to 100 nanoseconds like that. So forget about people from other countries. They used to run for 20, 30 nanoseconds. Then, with the advent of graphics processing unit, okay, so GPU flash, you have now excellent. Now I'm telling you that buy one machine, one desktop with i7 processor. Okay, with i7 processor, you buy, and then with that, you buy one graphics card, GPU card. You can buy, I'm writing it on the chat box, RTX 2080 Ti. You buy this one costs 1,05,000. If you don't have that much money, you can buy RTX 2060. Buy this thing. RTX 2080 Ti cost you 1,05,000. Okay, you can get it within 1 lakh. And RTX 2060 Super will cost you around 45,000. Okay. Now, what is the advantage? These graphics card, for example, RTX 2080 Ti has 4,300 cores available. So, although you have only i7 processor, you will use only one processor. And all these calculations, this parallelization will be done in the code that is available in your graphics card. So now you have a system that contains 4,305, almost 4,400 code available. So it will behave like a mini supercomputer. And everything you can get it within 2 lakh, or maybe 2.5 lakh maximum. You should buy one UPS also. That's all. So now, in this system, you can run a moderate size coding for microsecond time scale. For a big coding, you can of course run it for a couple of 500 nanoseconds or half microsecond, of course you can run. It's a now level playing field. So what happened in 2012? So then, actually, let me tell you a story about one guy. This is called, his name is B.E. Shaw. Okay? So Dave Shaw, he was a professor in Columbia University, computer science department. Okay. He has a company, he has a branch in India also. It's called Dayspace. Okay, D Shaw. In Hyderabad, he has So D Shaw then, in 90s actually, he said, enough is enough. I think I should earn money. He was a very brilliant guy. So he found his company and basically share market. Okay. Even so, think about it. Even in 2008, when the subprime crisis was there, still he could give profit to his customer. That was his thing. But he hires only the most brilliant people. Okay, he goes to say this university. Okay, only this Ivy League university, and asks them, okay, in your department, who is the mathematics student available? And they say, okay, this guy is the most, mad mathematical genius. Then he hire him, and he does not hesitate to offer $500,000 salary to his employee actually. Okay, starting salary. So he earned a lot of money. And then he said, what is the purpose of earning money? I have to solve some real world problem. I should go into the drug discovery thing. Now, for drug discovery, you have to study the structure, study the dynamics of the protein. So then he developed this company with that money, whatever he has. Okay, so he uses there and make this company. He saw research. And he hired a lot of people from mechanical, electrical, computer science, and make his own supercomputer. It is called Anton. Okay, I write it. It is called Anton. First computer he made, but it's a specially designed. It can only perform in the simulation. Okay, and this format is different, of course. And he first time shows the simulation for millisecond time scale. That is in 2012. And we are all awestruck. Oh my God, someone simulated millisecond simulation. That paper was published in Science actually. So first time he shows the protein folding and unfolding. That exactly even you can see in your experiment that he shows it. Okay. So now he has developed Anton 2. And he donated this Anton to Pittsburgh Supercomputing Center. Now he has kept the fastest one, Anton 2, for MD simulation. Okay. So in that time only he could publish this millisecond time scale and none of us. So then we started thinking about what we can do. We don't have that much money, we cannot work on it. Then we started working on developing Torsional model that I will talk tomorrow. Okay. To overcome that this time scale difference. But now, suddenly scientists started using the graphics card. This new generation, the older generation graphics card were very, that's not that good. I don't know whether you guys know or not. So previously, all those GTX cards, GTX 750, GTX 900, so probably you will know all those cards. So we used to use those cards. And we find that still it's better actually than the CPU that we are using. Okay, and the cost is very less. If you want to use multiple processors, okay, how many nodes you have to buy, and you need a huge electrical bill also. That will, your policy will not support it. That okay for you, and we are getting this high electric bill. But all this graphics card, when they come, we found that this graphics card required only 250 watt to 500 watt. That's all. So that's not high. Okay. So now, in 2020, the graphics card are so powerful. Like I said, P100 has more than 5,000 cores, one single graphics card. So if I buy 4 of these and use them parallelly, think about it. Okay, and it does not. Well, V100 is very costly. I'm telling you, V100 will cost you almost 10,000 US dollars. But what with RTX 2080 Ti is just 1 lakh. Now you cannot complain that. Well, I mean, you cannot simulate for 1 millisecond. That is true, but you can simulate for 1 microsecond. You can still compete with any researcher from good university in US because they also run simulation for microsecond one. Okay, so this gives us a very level playing field, and you cannot complain anymore. That okay, I don't have resources. Well, you need only 2.5 lakh. That's all. You can make a very good system. Okay.
Sir, one more question. Sir, what are the computer programs, I'm just saying an example, R, Python, which you are using, and some reference books, sir. Some reference book to get started.
The programming?
Programming.
So generally, these days, we move to Python. Okay, but for coding purposes, for molecular dynamics, for analysis, we use Python. Okay. Generally, when we develop a new method and implement it within Amber package, then we use C. Because that's the language they use. Even Charm has a very old-fashioned language. You know, they are still using Fortran 77. So when I was a postdoc, then we are transitioning from Fortran 77 to Fortran 95. But the base coding is NAMD. Okay, NAMD is the latest entrant into this field. So what Klaus Sultan did was that he hired computer guys, and he explained them everything, give them salary, and they said, okay, you guys write. So that is a very nicely written code. That is called NAMD. Okay. Even is also latest entry, so they are all written in C and very nicely written. You can understand. But if you look at Charm, this is not for the novice. If you are from the developing group only, you can understand the Charm. It's very cumbersome because people like me have written no. PGC, so it's very writing.
Sir, these are commercial packages or
NAMD GROMAX are free. Charm and Amber are paid. NAMD and GROMAX. Okay, but Amber you can get it free if you request them. If your director sign it that you don't have money, if you send them, they will give it. It's not like that they don't give it. Okay, you have to give the justification. They will give it free of cost.
what is the cost, sir? If so, if we need to pay, what is the cost?
Amber costs 600 USD. I would not suggest Charm because Charm is very difficult to handle. Okay, expert can only handle, but Amber is very easy to handle. A lot of TPRs are available, and it costs only 600 USD.
Okay, sir. Sir, book any book, sir. Book starting from basic.
This is principle of. So one book by this Andrew Leach. Andrew Leach, one book, and then another book by Thomas. These two books, I mean, these are the author's name. You can search their book. Those are the best book. Let me see. Actually, just give me a time. Let me find out. I can find it out. Just give me the reply. Let me paste here, okay? Thomas. So this is called molecular modeling, and so this is by this book is by Thomas Leak. What is that? Why I get it? By Thomas Leak, okay? He's a professor of Courant Institute of Mathematical Science, New York University. So you can read this book, Molecular Modeling and Simulation and Interdisciplinary Guide. It's one of the best books. I like it very much. And another book that I always read is, I also suggest my students also, Andrew Leach. I'm sending you the. Okay, so these two books actually you can study. Okay, so these two books, you can take it. So I give you the PDF link that is freely available, this Andrew Leach book. They can download it. Otherwise, they can buy it. Molecular Modeling, Principles and Applications, second edition, Andrew Leach. So both these books are very good. Okay, then there are other books are also there. Mark Tuckerman's book is there.
Sir, thank you. Sir, thank you for the suggestions and guidelines. So, yeah, sir. Thank you for this session. I would hand over the mic to Sahadev, sir. Sir, now can you please go ahead?
Thank you. This is a very wonderful session. We enjoy this session and we learn everything about the different types of algorithms and how it implements and their drawbacks, advantage. So thank you, Manu sir.
Thank you very much.
Yeah. Thank you, Sahadev.
Yeah, see you in the afternoon.
Sir, actually interpretation and max amalgamation, physics coming into picture, and ultimately computer simulation also coming into picture. So it was a wonderful session, sir. So I hope the participants have enjoyed it. So participants can approach sir if you want to carry out research over this field. So once again, on behalf of NIT Arunachal Pradesh and Atal AICT participants, I thank our expert sir, Professor Dr. Parimalkar sir, for this fourth session of this FDP. Thank you once again, sir.
Yeah,
thank you once again.
Thank you. See you in the afternoon.
Yes, sir. Yes,
okay.
sir.
Bye.
Yes, sir. And thank you, Sahadev sir, coming by within the short notice. Thank you for joining us as a chair. Thank you, Sahadev sir. And ultimately, thank you to all participants for participating. Thank you. Next session will be at 11 o'clock. So do join us then at around, join us by 10:55 or so. Thank you, participants.
Thank you, sir.